Welcome to Server-Lie, where ideas collide. In a world of tech, come take a ride. Artificial minds with hearts so bright. Join us on this journey, we're taking flight. With every bite, we're here to explore. Unlocking secrets, let's open the door. Server-Lie, let's make the magic flow. From data to dreams, we'll watch it grow. So grab your headphones, come join the fun. In the world of AI, we're never done.
Welcome to The Deep Dive, the place where we distill the complex world of research into high-impact knowledge. You know, for the last decade or so, AI has just been this constant whirlwind, right?
Yeah.
Deep learning brought incredible tools.
Absolutely. A total game changer.
But in just the last 2, maybe 3 years, something really fundamental seems to have shifted again. We're not just getting amazing results, but we're getting them, well, more efficiently. And that seems to be down to this quieter emerging paradigm around foundation models and something called self-supervised learning.
Yeah, that shift was critical because classical supervised learning, the old way, it really hit this massive wall, a very expensive one.
Right.
Think about it. To train a really good model traditionally, you needed millions of examples, labeled examples. Somebody had to pay humans to, draw boxes around cats or tag sentiments in text millions and millions of times.
And I guess that just gets exponentially harder with complex tasks like medical imaging, segmenting pixel by pixel.
Oh, definitely. Astronomical is the word. You need experts, highly trained people doing incredibly tedious work. And that cost, that human labor cost, it just became prohibitive. It limited what AI could even realistically tackle.
So it wasn't just about better algorithms anymore. It was about the sheer logistics, the data bottleneck.
Precisely. It became a data and labor problem more than anything else.
Okay, so our mission for this deep dive is to figure out how modern AI kind of broke free from that constraint. We need to unpack this two-stage pipeline that seems to dominate everything now, the method that uses the huge amounts of unlabeled data just floating around, pictures, text, you name it, to force the machine to learn general stuff on its own.
Reducing that need for expensive labels.
Exactly. It's about leveraging the abundant resource raw data to reduce the need for the scarce one human labels.
So let's start with the terms. They get thrown around a lot. Foundation model. What is that exactly? So a foundation model, think of it as the end result. It's a huge general-purpose model. It's been pre-trained on just massive amounts of data, usually unlabeled. The whole idea is it builds this versatile kind of base knowledge.
And then you can adapt it later.
Right. Adapt it for lots of different specific tasks down the line.
Got it. And the engine making that possible is self-supervised learning. SSL.
SSL. Yeah, it's pretty much what it sounds like. The model supervises itself. It cuts out the human annotator. So instead of needing external labels, the supervision signal, the thing it learns from, is generated automatically from the input data itself.
Okay, that's the key. Auto-generated labels. Which brings us to that core two-step process you mentioned. Step 1 is?
Step 1 is the pre-training stage. This is the heavy lifting part, computationally speaking. You take a very large neural network, think of it as a feature extractor, and you train it on just immense scales of raw, unlabeled data, like maybe 40 trillion words of text or billions of images.
Wow, okay. And it's not trying to solve a specific problem at this stage?
Nope, not at all. It's totally generic. If it's looking at text, it's just learning grammar, context, maybe some facts. If it's vision, it's learning about textures, shapes, how objects relate, the basic visual common sense of the world. It's learning the intrinsic structure of the data.
Okay, so it builds this general foundation.
Right.
And then step 2 is the adaptation stage, taking that pre-trained model and pointing it at a real problem.
Exactly. You take that model with all its learned knowledge kind of baked in, we call the learner parameters theta hat, and you apply it to your specific downstream task, like classifying medical scans or analyzing customer reviews.
And this is where the efficiency comes in, right? Because it's already learned so much.
Precisely. The model isn't starting from scratch. It has this huge head start. So the amount of labeled data you need for the second stage for the specific task is dramatically smaller. Yeah. You're not teaching a baby the world. You're like giving a grad student a specific research project.
It really boils down to resource availability, doesn't it?
Yeah.
There's just an ocean of unlabeled data out there, free for the taking, compared to the tiny trickle of high-quality labeled stuff.
Absolutely. It's just leveraging what we have in abundance.
What's fascinating here is, okay, if you don't have human labels, how do you actually tell the machine what to learn in that first pre-training stage? What's the goal?
Right. That's the clever part. You need to invent a task, something the computer can check itself on using only the raw data. This is called a pretext task.
A pretext task, like a puzzle.
Kind of, yeah.
Yeah.
It's a puzzle designed so that solving it forces the model to learn useful, general features about the data, features that capture that common sense we talked about.
Okay, so what do these puzzles look like?
Well, there are a few really effective strategies. One big one, especially in vision, is contrastive learning. You can think of it as a sort of positive-negative game.
That uses data augmentation, doesn't it?
Yeah.
Where you take an image and like automatically mess with it, crop it, flip it, change colors.
Exactly. You take one image, say a cat, you create two different random augmentations of that same cat picture. Those two versions are a positive pair. They look different, but fundamentally they're the same underlying thing.
Okay.
The model's job then is to learn a representation map these images into some feature space such that the representations of that positive pair end up close together.
Pulling similar things
That's
together.
true.
Makes sense.
Critically, that's not enough.
Yeah.
You also need negative pairs. These are augmentations from two different original images, say the cat, and a random picture of a car. The model has to push the representations of these negative pairs far apart simultaneously.
Ah, okay. Why is the pushing apart so important?
Because without it, the model could find a really lazy, useless solution. Just map every single image to the exact same point in the feature space. Everything would be close. We call that collapse. The negative pairs prevent this collapse by forcing the model to actually discriminate.
Got it. So it learns these things are alike and these other things are different, all without ever needing the label cat or car, just from the structure of the augmentations.
Exactly. It's learning similarity from the data itself. Another huge strategy, maybe even more dominant for the really big models now, is reconstruction and masking. This one was really inspired by how language models work.
Right, like masked language modeling.
Yeah.
Hiding words and making the model predict them.
Precisely. Fill in the blanks for text. The challenge was, how do you do that for images?
Yeah, an image is dense. It's not discrete words.
Well, one super successful approach is the Masked Autoencoder, or MAE. What they do is take an image, chop it into little patches, and then just delete a whole bunch of them, like a lot of them.
How many?
Often, like 75% of the image patches are just gone, missing.
75%. Wow. How can it possibly reconstruct from that?
That's the magic. That high masking ratio is the key. If you only mask, say, 10%, the model can just cheat by looking at the immediate neighboring pixels. It learns very local information. But when 75% is missing, it has to understand the bigger picture, the holistic structure of objects, the scene's layout, that visual common sense to have any hope of filling in those huge gaps.
So the difficulty forces it to learn more general, robust features, not just local stuff.
Exactly. It prevents the local cheating. And, before MAE, there were simpler visual pretext tasks, too, like showing the model a rotated image and making it predict the rotation angle. Was it 090 or 100 and 180 or 270 degrees?
So the label is just the rotation you applied.
Right. Or solving jigsaw puzzles, shuffling image patches, and making the model predict the correct original arrangement. Again, the shuffling pattern is the label.
Clever. And then, of course, the original idea came from language models. Strategy C.
Yep. Language models. The classic pre-training task there is usually predicting the next word in a sequence, given the words that came before it. It's called autoregressive modeling.
Like finishing a sentence.
Basically, yeah. It learns grammar, syntax, facts, reasoning abilities, all by just predicting what word comes next, over and over, on trillions of words of text.
Okay, so stepping back from the pre-training mechanics, what does this whole two-stage foundation model pipeline actually mean for people trying to use AI? What's the payoff?
If we connect this to the bigger picture, the real value prop is efficient knowledge transfer. That pre-trained model built with SSL already has this deep, intrinsic understanding of language or vision. It knows the patterns, the rules, the physics of its domain.
So when you go to apply it to a new specific task,
You need way fewer labeled examples to get good performance because you're not starting from zero. You're leveraging all that pre-learned knowledge. That's the efficiency gain. Cheaper, faster deployment of AI for new problems.
makes sense. And when we actually do that adaptation in step 2, there are different ways to go about it, right? Like linear probing.
Right. Linear probing is kind of the simplest method. You take your big pre-trained feature extractor, the violet hat part, and you freeze it. lock its weights completely.
So it can't learn anything new.
Correct. You only train a single, simple linear layer, the classifier dollars on top of it, using your small labeled dataset for the new task.
Why freeze the main network? Seems counterintuitive.
It's mainly used as a diagnostic, a test. If you can get, say, 90% accuracy on a new task by just training that tiny linear layer on top of the frozen features, it tells you the original pre-trained representation is really good and captures highly transferable knowledge. It measures the quality of the foundation.
Okay, a quality check. But if you want the absolute best performance on the new task,
Then you usually move to fine-tuning. Here, you don't freeze the pre-trained weights. You use them as a really good starting point, an initialization. But then you train everything, the original feature extractor and the new task layer together on the small labeled data set.
so you let the whole network adapt a bit more to the specifics of the new problem.
Exactly. You allow it to specialize, potentially squeezing out better performance than just probing.
And then there's the stuff that feels almost like science fiction, especially with the big language models. Zero-shot and in-context learning.
Yeah, this is where foundation models really shine. Zero-shot adaptation means you adapt to a new task using 0 new labeled examples for that specific task.
How is that even possible?
You basically just ask the model the question directly, framed in natural language. For instance, you give it a movie review and prompt it. Sentiment, positive, negative. The model, with its vast understanding of language, can often just generate the correct answer based on the patterns it learned during pre-training.
So it's applying its general knowledge to a task it's never been explicitly trained for.
Right. And few-shot in context learning is maybe even wilder. That's the party trick where you show the model how to do something within the prompt itself.
Like giving it examples right before the question.
Exactly. You could write in the prompt, translate English to French, sea otter equals loutre de mer, cheese, fromage, dog. The model sees the pattern from the examples you provided in the context and figures out you want it to translate dog. It learns the task on the fly, just from the prompt, without any weight updates.
That's incredible flexibility. It's like it's reasoning from the examples.
It certainly looks like it. It's leveraging that massive pre-trained knowledge base in very dynamic ways.
So ultimately, this whole push towards self-supervised learning, it feels like AI trying to grasp what Yann LeCun famously called the dark matter of intelligence, that huge amount of background knowledge we humans just absorb about how the world works.
I think that's a great way to put it. It's about learning the implicit rules. Why can a human learn to drive a car in maybe 20 hours? Because we already understand physics, objects, prediction. We have common sense.
Whereas old school AI might need millions of tries in a simulator starting from nothing.
Exactly. SSL is trying to give AI that common sense foundation, that head start, by letting it just observe massive amounts of data, learning the underlying structure of the world before tackling specific goals.
Here's where it gets really interesting. Because while this idea of filling in the gaps, predicting missing words in text, or reconstructing masked image patches like with MAE, well, that's been unbelievably successful, especially for language. There's a really significant caveat mentioned in the research we looked at. It seems that teaching a machine to learn about the visual world purely by, say, watching videos and trying to predict what happens next frame by frame, mastering that dynamic temporal prediction, that hasn't really worked yet, not at scale.
That's true. Predicting the future, even the very near future in video, seems to be a much harder self-supervised task than filling in static gaps.
Which leaves us with this really provocative question, doesn't it? Is filling in static blanks in text or images actually enough to build truly general intelligence? Or is mastering the prediction of dynamic change, understanding what happens next, the essential missing piece that these systems still need to conquer?